So thank you very much for inviting me to this conference. You may notice that I slightly changed the title of this talk, which is now Assimilation of Remote Sensing by Flood Extent and Soil Moisture Data into Coupled Models. So I find it interesting to contrast soil moisture and flood extent data assimilation for stream flow predictions, because we have seen yesterday also that sometimes it's not straightforward to improve stream flow predictions when you assimilate data from just the first few centimeters of your soil. In fact, the results I'm going to show you are from a study that we did for the European Space Agency in collaboration with the University of Bristol and TU Vienna. The purpose was to evaluate the usefulness of different Earth observation data sets for catchment hydrology. So there are two research questions. One concerning more the methodology of finding a good, rigorous approach for efficiently combining soil moisture and flood extent data derived from remote sensing into hydraulic models for improved stream flow predictions. And then more a process hydrology question, I would say, where we want to analyze what's actually the benefit of assimilating these two data sets into the models. So again, as it was said yesterday, it's not so straightforward to improve stream flow predictions by assimilating soil moisture. And one reason is, of course, that it's difficult to propagate this information through your model so that the improvements of the soil moisture in the first centimeters of soil actually impact the stream flow predictions of your model. So one way to address this problem is to couple your hydrological model to a hydraulic model that will convert stream flow into flood extent, and then to use flood extent observations from satellites to improve this model component. And so there are different sensors available to get this information you need. So soil moisture for improving your hydrological model, and flood extent to improve your hydraulic model. And the hypothesis of our work is that by assimilating both data sets, we can improve stream flow predictions more significantly. So the rationale for this approach is given by these kind of plots that you can get from field hydrologists in basically every mesoscale catchment from around the world. So we have a very typical relationship between discharge on the x-axis and saturation degree or soil moisture on the y-axis. You see that for a large part of the year, soil moisture is changing, but this doesn't have any impact really on a stream flow. It's only when you reach these critical thresholds that correspond to field capacity that really runoff production starts. So the idea here is that soil moisture helps you, of course, to better monitor the antecedent moisture conditions of your catchment. But once you reach these critical thresholds, soil moisture data doesn't help you that much anymore to better predict stream flow. And in this case, you better switch to other data sets, like ideally, of course, in situ discharge measurements, or like in our case here, flood extent observed by satellite sensors. So we set up a methodology that can be applied or should be applied to applicable to any catchment in the world, using by default satellite data to force your model and to calibrate it, and also to do these periodical updates. So it's a model cascade. You have the hydrological model and the hydraulic model. Then you have the Ensemble Generation, the processing of the satellite data, and the actual data assimilation. We use for this as a hydrological model the Superflex that some people of you may know. It was developed by Fenicia et al. In fact, the idea behind this model is that it is just a library of different components that are reservoirs, split and junction functions, and convolution functions. And by combining these elements, it should give process hydrologists the possibility to test different hypotheses of catchment functioning. And this framework is also very interesting for remote sensing data assimilation, because it's also possible to develop a model structure that fits the characteristics of the satellite data that you are planning to assimilate. And also, you can make sure that you have a better possibility to propagate your assimilated data sets through your model to the outlet so that you can better impact also the stream flow predictions. For the hydraulic component in this cascade, we use the Leaf-Flood FP model that was developed at Bristol University. The interesting thing of this model for our project is that you don't need very precise information of riverbed geometry, since riverbed geometry can be obtained through calibration. So when you have large collections of remote sensing data sets, you can use these to calibrate also the river channel. And this makes it, of course, an interesting model to apply in data poor regions where you need to rely on satellite data to calibrate your model. Then once you have set up your model and calibrated the two components, before you can start with the data assimilation, of course, you have first to estimate the model uncertainty. And in this first experiment, we made the strong assumption that all the uncertainty comes from the precipitation data. So we just log normally distribute, or we have an error term that is log normally distributed that we apply to the precipitation data that in this case was obtained from the ERA interim product from the ECMWF. And we use this then ensemble of precipitation records and also air temperature records to force the model. And this gives us on the middle plot the uncertainty of the soil moisture, and also in the end the uncertainty of the discharge. And then this ensemble of stream flow records is used as boundary condition of the hydraulic model and helps you or allows you to generate an ensemble of flood extent maps that you can then compare to the flood extent that you can obtain through remote sensing. So in this study we used 3 data sets. For the soil moisture part we used the ASCAT scatterometer, and in this case the product that was or is generated routinely by TU Vienna. And we also used the AMSR-E radiometer data that is the data set from the University of Amsterdam. For the flood extent, in this case we used the Envisat ASA white sword product. But in the meantime, there are many other missions that can be considered, so that while in the past it was you needed to be really lucky to get any observations of flood extent, by using this data from different missions, and especially using now the data from the recent Sentinel-1 mission of the European Space Agency, it becomes much more straightforward to get flood extent observations from space. I will only briefly describe how the soil moisture data was processed. I think especially for those that were here in the beginning of the week, they probably got much more information on this. So we used a snow masking because that was what really hampered the use for this data set in our case studies. Then we upscaled or downscaled it to the model grid. For us, the model grid was fixed in such a way that we could easily integrate the ERA interim reanalysis product as forcing data. And so we use this as the reference grid and upscaled or downscaled other data products from satellite remote sensing to match this grid. Then we use the filter that was proposed by the team of Wagner et al. To convert surface soil moisture to root zone soil moisture using a timescale coefficient. And in the end, we performed the CDF matching to have the same climatology in the remote sensing product and the model. A very essential part in whenever you assimilate, of course, satellite data, but any other type of data is, of course, to characterize the uncertainties of your product. In this case, also we did something very classical. We used the triple collocation method and used as a triplet for this 3 independent data sets, which are the modeled soil moisture, the moisture obtained from AMSR-E, and the one from ASCAT, to get an estimate of the uncertainty of the soil moisture in the space of the model. Now, in fact, it's quite easy to interpret microwave remote sensing image to extract flood extent. What is a little bit more complicated is that to also estimate the uncertainty of this estimate. And the methodology that we developed in our group first consists in fitting a gamma type curve to the histogram of backscatter values that we obtained from remote sensing. So typically this is this first distribution of pixel values with very low backscatter values that represent open water. So this is having a very low backscatter compared to the dry surfaces of your floodplain. And the idea here is to fit this gamma curve in such a way that you minimize the difference between your analytical PDF and the empirical histogram. And once you have done this, you can in fact directly infer the conditional probabilities. So what is the probability of having water on a given pixel given its backscatter value? And this helps you in the end to convert what is typically available as a binary map of flooded and non-flooded pixel into a flood probability map that is much more useful for data assimilation, of course. Now we try to evaluate if the probabilities that we obtain reflect the true uncertainty of the remote sensing derived flood extent map. And here it's important to differentiate between the classification uncertainty and the uncertainty that comes from the sensor, because there are some areas, of course, in the floodplain, such as within the built-up settlements or under vegetated canopies, or in regions where you have strong topography, where you have shadow and layover effects, where the satellite simply cannot give you any useful information. So it's first important to mask out all these errors or all these areas where you know that the satellite cannot give you any useful information on flood extent, and then to focus on the remaining pixels to estimate then the uncertainty that comes from the classification algorithm. And the validation we perform is using these QQ plots where you have where you can use as a benchmark for a flood extent that can be obtained through aerial photography to see if the probabilities from your that you obtain from your remote sensing product give you a close enough estimate of the real probabilities of having a flood on a given pixel. Then concerning the assimilation schemes, we used a particle filter. I think most of you will be more familiar with the Ensemble filter and its many different variants and other even more developed data assimilation schemes. We use the particle filter because it gives us some flexibility concerning the description of the uncertainties of your input data sets. This is maybe not so much of an issue for soil moisture, but we will see later that it's something that can become very problematic when assimilating a flood extent map into a hydraulic model. The idea of the particle filter is that you are starting with a set of ensemble members or particles that give you an estimate of soil moisture, and then you weight these particles given their closeness to the observation. So, for example, in this case, this light blue dot represents the soil moisture that is observed from the satellite. The red line is, in fact, the parameterization that you obtained through the triple collocation method. And then you give higher weights, of course, to the model realizations that are close to the observed value, and lower values to those that are quite far from it. And you do this updating of the model weights whenever a new satellite observation becomes available. Now the problem is often that you don't know exactly how many of the past observations you should still consider when recomputing new weights. So for this reason, we have added a new parameter to the weighting scheme, which is a time scale coefficient, and in fact it's an exponential decline that will consider more or less data from the past to update these weights. And we will measure also what is the impact of this timescale parameter on your final results. In the end, we have a weight for every grid point of your catchment, and since we are only interested in stream flow, what we did is we lumped, in some sense, the weights that we obtained for the different grid points, and applied then the weighted mean to the different stream flow realizations from the model to compute a weighted mean also of stream flow. For the flood extent assimilation, we could not simply assume a Gaussian distribution about around an observed flood extent product from space. In fact, we have only a binary map from the model, so it's just the hydraulic model tells us if a given pixel or grid point is flooded or not, but we are not using the water stage data from the model, since this is not what is observable from space. So in fact, what we had to do was we had to assume a binomial likelihood PDF. So in fact, it just compares the binary flood map obtained from your model with the flood probability of map that you obtained from satellite observations, and you combine these two data sets to compute an aggregated weight for every model realization, so every ensemble member. Now this was the methodology part of this talk. Now I would like to pass to the case study where we applied this methodology to measure the impact that the soil moisture and flood extent data assimilation can have on stream flow predictions. And we used two very different catchments for evaluating this methodology. The first one is the Severn catchment in the United Kingdom, and then the second one is the Zambezi in southern Africa. And in both cases, we used as meteorological forcings the ERA interim product, and also used in situ discharge records for calibrating the two components of the model cascade. So for the Severn, we set up first a hydrological model for the upstream part of the catchment at the gauging station Bewdley, which is here. And for the downstream part, we set up Liftflood FP until the gauging station of Howe Bridge. Of course, there are different other tributaries that could have been modeled as well, but to simplify the approach, we took for these other tributaries the in situ measured discharge to force the model. So in fact, we have then the only modeled data at the Bewdley gauging station, which is the main contributing area of the Severn, and for the rest we use the in situ measured discharge to force the hydraulic model. So we set up the hydrological model at the Bewdley station. We set up a model structure that reflects the main processes of rainfall run, or the main rainfall runoff transformation processes of this catchment. The model is calibrated using the in situ data from Bewdley over the time period 2003 to 2006. The assimilation was then performed over the entire period 2007-2012 using the daily ASCAT and AMSR-E derived soil moisture products. So even if we are not using any in situ measured precipitation to force the model, but we use the ERA interim product, we found that in the validation period we have already a Nash flat cliff of 0.74, which is a very good value given the input data especially. And also something that's interesting and important is that we measured the correlation between the soil moisture state variable and the stream flow, which is also quite high. It shows us that there is actually a possibility to improve stream flow data by periodically updating the soil moisture from the model. If this correlation would be very low, then the chances of success would be from the beginning rather small. So here are the results. You see different types of plots on the top. You can see how efficiency varies over the years. In fact, efficiency just expresses what is the improvement with respect to the open loop simulation. So every positive value is an improvement, negative values are decreases in performance, and 0 just means that you don't change at all the open loop simulation. So the interesting thing here is that you see that there are different specific periods in each year where you can improve stream flow predictions using soil moisture data sets, and there are other periods where at best you remain close to the open loop, and there is even a slight risk of decreasing the performance of the model. And we see these specific time periods each year. The different colors just represent different configurations of the filter. So in fact, what we change is this memory effect. We wanted to see if it makes sense to take into account all past informations, or if we should only take into account information from a certain number of days preceding the assimilation attempt. And we could see that in our case, the best results were obtained when we used as a time scale coefficient of the exponential decline a value of 3 days. On the middle graph, you see then the accumulated efficiency since the beginning of the experiment, and you can see that in the end, overall, we get improvements up to something like 25% with respect to the open loop, which is about a good result in my case, in my opinion. We redid the same experiment with AMSR-E data, and with AMSR-E data, we could already see after the triple collocation that the uncertainties in this area were much higher than for the ASCAT product. So we were already not expecting to have the same magnitude of improvements with this product than we had previously obtained with the ASCAT product. But still, we can see something that looks relatively similar to what we saw before for the ASCAT. So again, you have very specific periods in the year where you improve your discharge forecasts or simulations using soil moisture, and others where it's not possible. But in the end, if you aggregate or accumulate your efficiency over the entire period, you see that you have hardly any improvement on discharge. So we wanted to know a little bit better what's the reason that in some periods of the year this works and other reasons it doesn't seem to work. And for this we split the year into the 12 months, and we computed the average efficiency in each period. And we found out that the improvements are mostly obtained in these summer months from May to September. In case of ASCAT, and only from July to September for AMSR-E. And when at the same time you look at the precipitation and evapotranspiration records in the same periods, you can see that improvements are obtained when you have high precipitation and in the same time high evapotranspiration. And this makes sense when you remember the plot I showed you in the beginning when you had discharge versus soil moisture. So it's really in these periods where you have a relatively high uncertainty on soil moisture. So it makes sense then to assimilate the satellite products to do these updates of your model. Whereas in the winter periods, the uncertainty in soil moisture is relatively low, because when evaporation is very low, the soil moisture remains at a very high level for the entire winter period, and there's every decently calibrated model is able to know that you remain close to not exactly saturation, but something close to it. So the uncertainty of the soil moisture is relatively small in the model. But it's then in this, let's say, wet and rainy periods, or wet and hot periods, where in fact you can make a difference by assimilating soil moisture, because you can tell the model how close you are to the critical thresholds that contribute to the generation of a flood peak. Now the next step was to assimilate the flood extent of products that you obtained from remote sensing, and there was one major flood event on the Severn in July 2007. So the good thing is that this was exactly in this period where I showed you beforehand, where you also can make some improvements with soil moisture data assimilation. So it's possible now to contrast what is the improvement you obtained by assimilating soil moisture, and what is the improvement when assimilating directly flood extent into this model cascade. In fact, one thing we had to do beforehand was that we had to drastically reduce the number of observation points that we assimilate into the model, because these high-resolution products, they just give you too much information for your model. And so what we wanted to first do was to find the most informative data points. So for this, we applied a number of masks by, for example, restricting your analysis to the area of your catchment where there is a possibility of flooding. So for this, we use the hand product, so height above nearest drainage. So when you are far from your drainage, there's anyway no possibility of flooding, and it makes no sense to consider these points. Before that, we used a correlation layer that we obtained from the TU Vienna. In fact, it shows you what are the areas in where the satellite can give you some information on flood extent, and what are those where there is, from a historical perspective, no possibility to detect flood extent. For example, the vegetated areas and the urban areas. And also, we used the model to further reduce the number of observation points, because in all those areas where the model runs agree, so for example, all models say that a given pixel is flooded, or they all agree that it's not flooded, the data assimilation will in this case not make a difference. So we restricted the analysis to those areas where there's a disagreement between the different ensemble members. So this is then from within the area covered by the model, those pixels where we consider the flood extent observation from the model. So this is this big flood event from 2007. So in the black line you have the observed discharge. The gray is the open loop simulation, and the green is the one that was obtained when assimilating soil moisture. So for the first part of the flood peak, we didn't have any information on flood extent. It's only late in the event, so at the end of July, where two satellite acquisitions were available for updating the model. And what we could see is that the soil moisture data assimilation in this case would have even led to a significant decrease in model performance. But the flood extent data assimilation, on the other hand, helped us to slightly improve the stream flow predictions. So maybe if you make a zoom in on this event, and on the lower graph you see the efficiency over the event, you see that for some hours after the acquisitions, the flood extent product would have helped you to significantly improve the open loop with respect to the open loop simulations, whereas during the event or during the flood event, soil moisture data assimilation would not have provided you with any big benefits. We also evaluated these results on a gauge that was located a little bit downstream to see if we can confirm these results. And also there at the gauge and sections load, we could see that the efficiency of the flood extent data assimilation during the event was up to 38%. But of course, the improvement was vanished quite quickly as the flood progressed. The information from the past was not anymore useful, and the efficiency got again close to zero. So we repeated the same exercise in the Zambezi catchment in Southern Africa, where we had stream flow recordings from at the gauging stations of TT. Here, the main issue was that this part of the Zambezi basin is heavily regulated by a dam. So in some sense, it makes it easier for us to simulate, for example, stream flow during the summer period, because it basically remains at a constant level. And on the other hand, it makes it difficult to predict the peaks, because we don't know how the dam is operated in the event of a flood. And you can see even before starting any assimilation attempt that by just looking at the discharge records at TT, that there are some anthropogenic influences that we will not be able to reproduce in our model. When you look at the rain season in 2009, when you look at the rainfall amount, it's more or less the same or even higher than in the previous years, but the discharge that is measured is comparatively low. So it's a challenge to really do any meaningful stream flow predictions in this basin if you don't have an idea how the dam is operated. Nevertheless, we tried again to set up a hydrological model in the same way like we did before. In this case, the Nash Satellite cliff in the validation period is 0.66, so quite low. Surprisingly, though, the correlation between soil moisture and discharge is quite high. So there is nevertheless the possibility to improve the stream flow predictions using soil moisture data. And the hydraulic model was calibrated by NASA using altimeter-derived water levels. So here you see the results when you pre-process the different soil moisture products. So after you apply the sequence of pre-processing steps, there's a rather good agreement between the model and the satellite products in the case of ASCAT. But for AMSR-E, we did not manage to get a good fit between the model and the data set. And for this reason, we finally decided not to consider AMSR-E data in this case. It was also by comparing it to the soil moisture product from ERA Interim that we could see that there was a very high correlation between this product and the ASCAT product, but a very low correlation with the AMSR-E. So for this reason, AMSR-E data was not assimilated in this case. And when you now look at how the efficiency changes over the year, you see again a seasonal pattern that we saw before for the Severn as well. So again, some specific periods where you have an improvement and others where it's not possible. In this case, it's more a trivial result because, as I mentioned before, for a large part of the year, stream flow remains at a rather constant level. So it makes it's obvious that in this case you cannot improve the results. Again, when we look at those periods where we achieve an improvement, we see that it's again those where we have high evaporation rates and high precipitation. So it means high uncertainty on soil moisture and high uncertainty on stream flow. For the Zambezi, we considered a flood event that took place in February 2008, where we had the sequence of 3 Envisat images that gave us information on the flood probabilities. Again, we applied these different masks to restrict our analysis to the most informative grid points and compared then the assimilation of these 2 products into the model. Again, we could see that on the lower graph that you have an improvement up to 75% with respect to the open loop. But in this case, this is not very telling because already the open loop was very close to the observed discharge. So this is a little bit misleading to think that the improvement is that high. Again, you see that of course the improvement when you assimilate flood extent doesn't persist very long. So it's only within a few days after the image acquisition that you can still achieve an improvement, when later it's not having any significant impact anymore, and it's again more worthwhile to switch to another product such as soil moisture. So the conclusions for this work, these are very preliminary conclusions, since there are still many elements that need to be reconsidered. But one thing that we seem to understand is that assimilation of remote sensing derived soil moisture products can indeed improve discharge predictions, but this is restricted to specific time periods. We also see that the efficiency, of course, clearly depends not only on the satellite product, but also on the settings of the filter and also the climatology of the catchment. So there might be some catchments where soil moisture data assimilation isn't worth considering. Concerning the assimilation of flood extent, we could see that as expected or hypothesized at the beginning, the flood extent data assimilation outperforms the soil moisture data assimilation during the storm event, but it doesn't have when soils are saturated and soil moisture is not giving us useful information. So the idea here is that they provide really complementary information that can be used for discharge predictions. Maybe these are just a few suggestions how what can be improved in the future. as I said, there are really so many processing steps involved that all of them basically need to be revised and improved. And then maybe like somebody yesterday said that data assimilation works nice in theory, but so far not really in practice, at least when you deal with satellite products. But maybe when we improve all these different processing elements, maybe then it will be possible to get also the same improvement levels than we obtained previously with synthetically generated data sets and synthetic experiments. So thank you very much for your attention.
Thank you very much, Patrick, for the very good talk. And a bit optimistic as well. Question?
Thank you for your talk. It was not very clear to me how you assimilate soil moisture into your model. Is lumped? Or?
No, the model is not lumped. It's in fact the soil layer is distributed in space. It's only then the deeper soil layers that are lumped. You have these two, maybe.
How do you get parameters for it?
Wait, I will just show you here. So there you have a lump part and you have a distributed part. So the distributed part gives you then for each grid point a soil moisture estimate. So for each grid point you compute the weight, and then as I mentioned it later, we aggregated this weight and applied it then on the overall stream flow recordings. No, we simply have one parameter set for the whole catchment. It's the variability in soil moisture comes entirely from the precipitation variability, not from the catchment characteristics that change over as well. You don't have this data all the time.
Any more questions? Right, thank you very much, Patrick. And then we move to the last talk of the workshop, and that will be given by one of the